Polar review and rectangular coordinate connections with polar as quickly as possible for a 5-page worksheet. Number one, polar points. So polar points are in r comma theta instead of x comma y. So if we name this point P in 3 different ways in polar form, r is 5 and theta is pi over 3. That one's pretty obvious. The second one, 5 comma 7 pi over 3, that occurs because 7 pi over 3 is coterminal with pi over 3, because if we just go another 2 pi or another 360 degrees around, we'll end up landing exactly in the same spot at 7 pi over 3 in terms of theta, and then 5 is still the radius. We could also go negative 5 comma 4 pi over 3. That's because 4 pi over 3 is 180 degrees or pi away, so that is down in this direction over here. But since we say negative 5, that means it flips the direction of our radius. So negative 5, 4 pi over 3 would be 4 pi over 3 is down here, but negative 5 makes it go exactly the same distance right back here to where P was. Also, I gave you the rectangular coordinates, 5 halves, comma, 5 root 3 over 2 for x comma y, just in case you want them. Okay, circles. A, r equals 4. Notice that for the first two, I showed converting r into x squared plus y squared equals 16. Notice that we have some things up at the top that you really should pay attention to. X squared plus y squared equals r squared, which means r equals square root of x squared plus y squared. X equals r cosine theta, y equals r sine theta, and then of course x over r equals cosine theta, y over r equals sine theta, and y over x equals tangent theta. Those are things that you're going to want to know. So x squared plus y squared equals 16. That means that the center's at 0, 0, and the radius is 4. So if we look at r equals 4, and I graph the circle, notice it starts here and then goes all the way around like so, and at 2 pi it finishes. So it's just mapping the radius 4 all the way around as the angle goes around. If we look at the second problem, r equals 3 cosine theta. So r equals 3 cosine theta. I showed algebraically what that looks like in rectangular coordinates. It's actually kind of a nightmare to do. You have to convert things, complete the square. So that's where x squared minus 3x plus 1.5 squared comes from. Then if I write it in the circle form that we're used to, that's x minus 1.5 squared plus y squared equals 1.5 squared. So this should be a circle with center 1.5 comma 0 and radius at 1.5. So if I look, I want my a to be 3 in this case. So if I look and I graph this, that's exactly what happens. But if you notice, it finishes graphing at pi. So it basically just traces itself over more than one time if you go past pi. That's going to be important, especially for calculus purposes, because when we're finding areas and things like that, you don't want to map over itself more than once. So from 0 to pi, this maps like so. Letter C, 5 sine theta. I'll do 5 sine theta first, and then we'll do negative 5 sine theta. So notice that sine graphs start at the origin, which makes sense because sine of 0 is 0, whereas cosine graphs started at whatever the length of the radius is, and that makes sense because cosine of 0 is 1. So if we graph this, again, notice that sine finishes its graph at pi and then just maps over itself again. But notice if I make this negative 5, it's going to graph below the axis. So that's important to realize. Letter C will graph below the axis because we have negative 5. And notice that it's negative 5 times sine of theta. So since sine of, let's say, pi over 6 would be over here, it's going to map it in the opposite direction because negative 5 times the angle sine of pi over 6 is 1/2, that should mean that we end up at negative 2.5 when I have sine of pi over 6. Now let's say negative 4 cosine. That's going to be a circle over here. Notice it starts at negative 4, and then it goes around. Once again, it just maps over itself after pi. So hopefully you graphed all of those things. The minimum interval for creating a circle of r equals c is 2 pi, so you have to go a full distance of 2 pi radians to get that. But if you have a circle a cosine theta or a sine theta equals r, then it's just pi. Cardioids, r equals a plus or minus a cosine theta, or r equals a plus or minus a sine theta. Note that a is the same in both spots. So if we go to cardioids, the first problem on our sheet is, 2 plus 2 cosine theta. So if I graph this, it's going to look kind of like a heart, if we remember from pre-calculus. Notice again, it starts at r equals 4. That would make sense because 2 plus 2 cosine of 0 is 2 plus 2, which is 4. And then it kind of maps around and goes like so. If I say 3 minus 3 cosine theta, that's part B. It maps starting at 0, which again makes sense because 3 minus 3 times 1 should be 0. And then it graphs around. At pi, it's going to be 3 minus negative 3, which is 6. And so if you just kind of trace where pi over 6, pi over 3, and so on are, you'll get a pretty decent approximation of what it looks like. So that is our cardioid, 3 minus 3 cosine theta. Now if we do 4 minus 4 sine theta, here's our graph. Notice that 4 minus 4 sine theta will start at 4 because 4 minus 0 is 4. So it starts here, maps like so, and goes around. Notice that all of these graphs take a full 2 pi in order to do it. If I change this to a plus sign and make it 3 plus 3 sine theta, like part D, it's going to start at 3. It's going to get bigger, maximizing at 6 at pi over 2. Then it goes back to 3. We'll go to 0 at 3 pi over 2, and then returns to 3 at 2 pi. Minimum interval needed to create a cardioid, 2 pi. Okay, Lima-Sohns. R equals a plus or minus b sine theta, or r equals a plus or minus b cosine theta. Recall that some have an inner loop and others have a dimple from pre-calculus. Notice that you're going to place a large dot where the graph begins, so hopefully you're doing that. Lima-Sohns. 2 plus 3 cosine theta. So if we have 2 plus 3 cosine theta, if we graph this, it's going to look something like that. Notice it will start at 5, which makes sense because 2 plus 3 equals 5. When we get to pi over 2, it's going to be at negative 1, or negative 1. I'm sorry, when we get to pi over 2, it's going to be at 2. And then when we get to pi, it's going to be all the way at negative 1. So notice when we're at negative 1, that means we're going backwards from being around pi. We're actually going this way. And then it recycles over here and lands at, when theta is 2 pi, we land back at 5. So if we have 3 minus 1 cosine theta, this one, it doesn't have an inner loop. This actually has a dimple, even though it doesn't really look like much of a dimple here. The further I make B, the more it looks like a dimple. So if I have b equals um, -1, it's a very minimal dimple here. Um, but if I graph this, it's going to start at 2 and then go like so. If I have r equals 2 minus 3 sine theta, I'm going to have an inner loop again. Notice I'm starting at 2 because when sine is 0, it's 0. Um, since it's minus 3, it gets closer to the axis. And then once we get past um, pi over 2, it's actually going to cycle back around. I'm sorry, at pi over 2, we actually are at -1 because 2 minus 3 is -1. So that means that at pi over 2, we're actually backwards down here. And then it cycles and finishes at 2 comma 2 pi for r comma theta. Then if we have 3 plus 1, we have one of these. This again has a dimple, even though it's not that easy to see. Um, but this is how the graph looks. It might be easier if we um, increase our A and B just to kind of show you what it looks like. So if we have this situation, the bigger A is and the closer B gets to A, then the more it looks like a dimple. Even though these are dimples, they're just really, really small dimples as you move along. So how do the relative values of A and B determine whether it's an inner loop or a dimple? If A is less than B, notice each time we had a loop, that occurred when we had parts A and C. When we had parts B and D, those were dimples. If A equaled B, it was a cardioid. And the minimum interval was 2 pi. Now let's go to roses. So roses are the final case that we're going to talk about. If we have r equals 3 cosine 4 theta, that's kind of nice looking. If we start here, notice it's going to start at 3 comma 0, and then it's going to continue to make a bunch of rose petals. Notice how many rose petals there are. There are 8 rose petals. Notice that the first rose petal that was made starts and it looks like it's going to be symmetric about the x-axis, um, but it will take the rest of the time to get all the way up to 2 pi in order for it to finally be filled. So that's 3 cosine of 4 theta. Now if we go 5 cosine of 3 theta, notice there are only 3 rose petals, so that's kind of an important distinction, and we will make that distinction as we move along. But again, notice that the first one is symmetric about the x-axis. Oh, wait a minute. Notice that it completed its entire cycle by pi. So once we got to pi, it then just started repeating on top of itself. So that's important to notice. In roses, there appears to be a different type of minimum interval necessary to create the rose, depending on probably what n is. And so if I look at this, if n is 4, I have 8 petals, but I only have 4 of them created, well, 3 full ones and 2 half ones created by pi. I'll go by about pi. But anytime, so at 5, I had 5 full petals. At 6, I have 5 full petals and 2 half petals, so that's a total of 6. But notice that it continues to go. Whereas if I have, um, oops, if I have, let's say 5 petals or 3 petals, I don't really need to go any further past pi. So that's kind of an important thing to keep in mind. Now let's go to sine. So 5 sine of 2 theta. It's going to start at 0 and work its way around. So notice again, n was 2, and there are 4 petals. This needed a full 2 pi in order to go all the way around. If I make this 4 sine of 3 theta, I have 3 petals, and again, it stops at pi. So this is kind of the same deal that we had with cosine. If I have 2 as my n, I have 2 of the petals, but I need to go all the way to 2 pi in order to get completely done. If I have 3 petals, it's all done by pi, basically. If I have n equals 4, I have 4 petals, but I need to continue going to get all 8. If I have 5 petals, I'm done by pi. And so that's kind of an important thing to keep in mind. When I have 6 as my n, I need to keep going so that I can get all 12 of my petals for sine of n. So here's all the information we need. Hopefully you kind of figured it out on your own. The number of petals, if n is odd, we have n petals. If n is even, we have 2n petals. If n is odd, we only need to go an interval of pi in order to go all the way around. But if n is even, we need 2 pi as our interval. Cosine roses are symmetric to the x-axis, the first petal anyway. And then the first petal for sine roses are given by theta equals pi over 2n. So if you go back here, notice that if I'm looking at my first petal, this one is symmetric to theta equals pi over 12, and notice that n was 6. This one, theta equals pi over 10. This one at n equals 4, theta equals pi over 8. This one at n equals 3, theta equals pi over 6. This one at n equals 2, theta equals pi over 4 is where it's symmetric for the first one. Problem 6. Graph these two things and find the intersection of the polar algebraically. So all the algebra is there. I'll come back and explain it in a minute. So if I graph these two things, I'll zoom out a little bit. If I graph these two things, 2 times 1 plus cosine theta and 2 sine theta, it appears we intersect twice. Also notice the blue one is done by pi, which was something that we figured out at the beginning. But the red one, which is a cardioid, it takes all of 2 pi in order to do it. So notice it appears to intersect at pi over 2 and pi for our theta, and at r equals 2 and r equals 0. So if I go here, I can solve this algebraically a couple different ways. I can convert everything into rectangular, which is what I did in red. So I converted cosine into x over r and sine into y over r, divided everything by 2, subtracted some stuff over, multiplied by r, realized that I get square root of x squared plus y squared equals y minus x. Then I squared both sides, the x squared plus y squared all goes away. I get negative 2xy or positive 2xy equals 0. That only works when x equals 0 or y equals 0. And then you have to go back and figure out when x and y equals 0. So in rectangular form, it's 0, 0, or 0, 2. For polar solving, I just subtract everything over, divide by 2. I get 1 equals sine theta minus cosine theta, and I figure out when that works. I'm only solving for 0 to 2 pi in this case, but that only works when sine equals 1 or cosine equals negative 1, because then negative 1 ends up equaling positive 1. So theta equals pi over 2 or pi, and then I end up figuring out what r is in those cases. So if I put pi over 2 into these equations, I end up getting 2 for my r. And if I put pi into these equations, I realize that r is 0. So that's how that works. Number 7, graph those two, find the intersection of the polar curves. This is not super easy, but here are 2 equations. So I graph those. It appears that we intersect at 0, 0 again for the rectangular coordinates. Which is going to be at 0, 0 for my polars as well. But let's kind of move along and see what happens there. So if I try to solve this using algebra, it takes a lot of work. So hopefully you can follow along. Um, where's my highlighter? Here we are. So I took the two things that we were given, and I ended up solving both of them for r squared. Then, and the reason I did this was I think solving this in the TI using function mode is actually really, really complicated. So then I set these two things equal to each other. So I got 2y equals 3r plus 3x. I replaced r with x squared plus y squared square root. Then I subtracted 3x from both sides. So I got 2y minus 3x equals 3 times x squared plus y squared square root. Then I squared both sides to get rid of the square root. So I have 4y squared minus 12xy plus 9x squared equals 9x squared plus 9y squared. Then the 9x squareds go away, and I subtracted everything to one side, so I have 0 equals 5y squared plus 12xy. I divided both sides by y. That's technically not a good idea if you don't remember that y equals 0 is being eliminated as a solution if you do that. But since I'm remembering that y equals 0 will be a solution, and when I graphed it, y equals 0 did have a solution. It was x equals 0, y equals 0. So I'm going to remember that that is actually a solution. So what I have here is I have 5y plus 12x equals 0. So when I solve that, I get y equals negative 12/5 x. I take that and I rewrite it as y over x equals negative 12 over 5, which, if I remember, y over x equals tangent of theta. That means tangent of theta equals negative 12/5. So then I did tangent of theta inverse in the calculator, and I found out that it was negative 1.176, which in 0 to 2 pi is going to be 1.966 about. So that's where I got 1.966. Now, how did I get 24/13 for r? Well, oh yeah, by the way, remember that theta equals 0 works, so 0, 0 will also work as one of my answers. So how did I get 24/13? Well, since tangent of theta equals negative 12/5, I drew the triangle, and I recognized that sine of theta in this particular triangle in the second quadrant, and I know it intersects in the second quadrant because I looked at the picture, um, it intersects and sine equals 12/13. So since sine equals 12/13, um, that means that r equals 24/13, because if I look right here, I saw that sine of theta times 2 equals r. So I take 12/13 and I multiply it by 2 to get 24/13. So 24/13 is r, theta is 1.966. If I wanted to get that in rectangular form, I get negative 120 over 169 and 288 over 169. And I basically just get that by subbing things in for x and y in these problems up here. Um, so my rectangular coordinates are 0, 0, and negative 120 over 169, 288 over 169. And then my r theta is 24/13, 1.966, and at 0, 0. So I wanted to kind of show you that all of this does actually work. So if I have negative 120 over 169 and 288 over 169, that's that red point right there, and that is where they intersect. Also notice that they intersect at 0, 0, which algebraically we eliminated as a solution, but we know that it geometrically is a solution. So when you divide by a variable, you have to be careful a little bit. So that's how that works out. And then the final question, problem 8 on your worksheet, is graph r equals 1 minus 2 sine theta. So we will do that. So I'll graph r equals 1 minus 2 sine theta. I could go from 0 to 2 pi, but the problem asks us to color things a little differently based on whether it is 5 pi over 6, or pi over 6 to 5 pi over 6, and 5 pi over 6 to 13 pi over 6. So notice that from pi over 6 to 5 pi over 6, we get the little part, the loop, and then we get the outer part otherwise. And it looks like I deleted those things, so I can't show you the red and the blue as I was supposed to without doing this. So this is your um, pi over 6 to 5 pi over 6, and this is your blue, just because that's what the problem says. And this is your 5 pi over 6 to 13 pi over 6. That is your blue in that case.